Let's talk about the derivatives of logarithmic functions. If f of x equals the natural log of x, now you may recall that the natural log of x is the same as the log base e of x. It's a base e logarithm. It tells us the exponent we need to raise e to get a certain result. Well, the derivative of the natural log of x is just 1 over x. If f of x is a logarithmic function with base a, that is a base other than e, so any base a but not base e, its derivative, f prime of x, is 1 over x times the natural log of a. Now, in both of these cases, the internal, or the argument of the log, is just x, so no derivative, or actually the derivative is 1. However, if our function is a logarithm that contains another function, so like the natural log of g of x, our derivative is 1 over that function, g of x, and we have to chain rule on the derivative of that internal function, so times g prime of x. That's for base e or natural logarithmic functions. If the function is a base a log with an argument that is a function that's differentiable, then f prime of x is 1 over g of x, very similar to log base a of x, times natural log of a, but we have to tack on the derivative of the internal function, or what we call the argument of the log. So let's look at some examples. Example 1, differentiate f of x equals the natural log of 5x. Now, since the argument, or the internal of the natural log, is a differentiable function, we have to tack on that derivative at the end. So we're looking at this rule. Okay, so we've got f prime of x is 1 over that function, 5x, times the derivative of that function. And in this case, it just so happens that those will reduce out, which happens sometimes, but not that often. So the answer to this derivative is just 1 over x. Example 2, find the derivative if y equals natural log of 8 minus 9x. So again, this argument, or the internal part of the natural log, is a differentiable function. So we're looking at this rule again. So our y prime, or our dy dx, is 1 over the function 8 minus 9x times the derivative, which is going to be a negative 9. So we're going to write negative 9 over 8 minus 9x. So negative 9 over 8 minus 9x. Now be careful. We cannot reduce this 9 with this 9. Okay, you can only reduce when everything is multiplication. Okay, and we got a subtraction, so no reducing is possible. So it's negative 9 over 8 minus 9x. Example number 3. Differentiate y equals the natural log of the absolute value of 7x squared minus 3x. Now you might say, why do we have absolute value bars here? Well, in the typical log function, y equals the natural log of x, x has to be a number bigger than 0. You can't take the logarithm of 0 or a negative number, because there's no number that you can raise e to get 0, okay, because e is about 2 point something. No matter what you do, you're going to get a positive number, and there's no number that you can raise e to that will give you a less than 0 number. Again, positive base, no matter the power, positive or negative, you're going to always get a positive number. However, this allows us to have a larger domain on our function, because we're saying you can get a negative in there because before we take that natural log, we're going to take its absolute value and make it positive. You can see it affects the derivative very little. So dy dx is 1 over 7x squared minus 3x times 14x minus 3. So it's 14x minus 3. All of that is over 7x squared minus 3x. And that is our final answer. Example 4. Find the derivative of the function y equals the natural log of the square root of x plus 20. So find dy dx. Again, we're looking at functions within the log that are differentiable, so we're still looking at this rule. Now what I would like to do here is what we always do when we have a square root, and that is we write this with a 1/2 power. So our dy dx is going to be 1 over x plus 20 to the 1/2 times the derivative of that, 1/2 x plus 20 to the 1/2 minus 1, and then the derivative of in there is 1. So we end up with 1 over 2. This 1/2 is going to end up 1 over 2, and then we've got x plus 20 to the negative 1/2, and x plus 20 to the positive 1/2. And when we move that to the denominator, x plus 20 to the 1/2 times x plus 20 to the 1/2, that's what we do with that negative exponent here, we're going to end up with 1 over 2 times x plus 20. And the reason for that is x plus 20 to the 1/2 times x plus 20 to the 1/2. Well, you add the 1/2 and the 1/2 and you get 1. So the final answer here is 1 over 2 times x plus 20. Now I want to show you an easier way to do this, or what I think is a little easier, using a property of logarithms. And what that property says, remember logs are exponents, okay? So you have a property that says when you raise a power to a power, you multiply those two powers. So I can multiply the 1/2 times that natural log, so I'm going to put it in the front, and that's going to be my new function to differentiate. So the property of log says the natural log of x to the p is the power times the natural log of x. So I've just brought my power to the front. So my dy dx, a little easier this time, is 1/2 times 1 over x plus 20, basically times 1, right? Because the derivative inside there is just 1. So you'll notice that it's the same answer, 1 over 2 times x plus 20. Example 5. Find the derivative of the function y equals the natural log of 3x to the 9th plus 7x all raised to the 5/3. And I'm definitely going to take advantage of the fact that because it's a log, I can put the multiplication of that exponent in the front. So I'm going to rewrite my function first. And now I'm going to use this rule for natural logs that have a function as the argument. There's something that I can take the derivative of. So it's times 1 over 3x to the 9th plus 7x times 27x to the 8th plus 7. So I'm using the power rule on that denominator. And so just multiplying what I have in the top, I'm just going to leave that 5 on the outside as a factor. And then I'll have a 3 and a 3x to the 9th plus 7x. So my final answer is 5 times 27x to the 8th plus 7, all of that divided by 3 times 3x to the 9th plus 7x. Example 6. Find the derivative of the function y equals negative 3x times the natural log of 8x plus 9. Now in this case, I have a product rule because I have a function with an x times a second function with an x. So this is our product rule. So if y is first times second, y prime is first times derivative of the second plus second times derivative of the first. So my first, I'm calling negative 3x. So my first prime, or the derivative of that, is negative 3. My second, I'm calling that natural log, 8x plus 9. So its derivative is 1 over 8x plus 9 times the derivative of that, which is 8. So simplified, that's 8 over 8x plus 9. And again, no simplifying. It won't simplify. You can't cancel those 8's out. You'll have a problem if you do. So my dy dx is my first, negative 3x. I'm going to keep it in parentheses just to keep them separated. Times the derivative of the second, 8 over 8x plus 9. Plus the second, natural log of 8x plus 9, times the derivative of the first, which is negative 3. And I'm just going to do a little bit of cleanup here, just some basic cleanup. I'm not going to make you get a common denominator or anything. I'm just going to go ahead and make that a minus 3 times the natural log of 8x plus 9. So my final answer is negative 24x over 8x plus 9, subtract 3 natural log of 8x plus 9. Number 7, find the derivative of the function s equals t to the 4th times the natural log of the absolute value of t. So here again we have two functions being multiplied, t to the 4th and the natural log of t. So my first function is t to the 4th, so my first function derivative is 4t cubed. My second function is the natural log of the absolute value of t, so my second function's derivative is 1 over t. So my derivative, ds dt, is first t to the 4th, derivative of the second, 1 over t, plus the second, natural log of the absolute value of t, times the derivative of the first, 4t cubed. So I can reduce a little bit. T into t to the 4th is going to leave me with a t to the 3rd. And I'm going to move this 4t to the 3rd to the front, 4t to the 3rd times the natural log of the absolute value of t. Okay, now I do need those absolute value bars there because it asks for the original second function. The second function had that natural log in it. Now this one's pretty easy to factor, although this is perfectly acceptable as an okay answer. I could easily take out a t cubed here and get 1 plus 4 times the natural log of the absolute value of t. And later on, when we do some applications, we do need to do some factoring on these things. So either one of those is fine. Example 8. Find the derivative of the following function. Y equals 9x to the 4th divided by the natural log of x. Well, this is a quotient. I have a numerator, 9x to the 4th. I have a denominator, natural log of x. The derivative of my numerator, 36x to the 3rd. The derivative of my denominator, 1 over x. When I have a quotient, my formula is denominator, derivative of the numerator, minus numerator, derivative of the denominator, over the denominator squared. So my dy dx, my derivative of y with respect to x, is the natural log of x times the derivative of the numerator, so that's denominator, times the derivative of the numerator, minus the numerator, 9x to the 4, derivative of the denominator, 1 over x, and all of that is over the original denominator, natural log of x, and look, you've got to put this in parentheses or brackets. That square, it's not the natural log of x squared, it's the natural log of x, then squared. So make sure you put parentheses or brackets there. Little bit of cleanup. I prefer to put the 36x to the third in the front so that it doesn't appear to be inside that natural log. Minus, have a little reducing here. That's going to leave me with an x to the third. So minus 9x to the third. And all of that is over the natural log of x, quantity squared. I might do a little bit of factoring here. By the way, this is a fine answer, okay? But just to practice with our factoring, I notice I have a 9 and an x cubed as a common factor. That's going to leave me with a 4 natural log of x minus 1. And all of that is over the natural log of x, quantity squared. So either of these answers is the final answer.